So in a previous video, we did a repair on this Ego light sent in to us by Stephen Rickstrew, and we showed that this light would not come on, no response. We'll do a really quick review here. We took the bottom cover off, all the screws, the hangers, the main bottom plate, take off our thermal pad, and then we could get to our module. We had to remove a lot of silicone potting to try to see what the problem was with this controller. We got to the point where we saw our first component failure. It was a 6-pin SOT23 device that was black around the white silicone where it had blown. We just tried to remove as much silicone as possible. Then we put some 99% alcohol in there to not only clean the board surface but let it soak through and release that silicone adhesion from the case that this controller is stuck in. I used my little vacuum pump, solder sucker, went around the pins on the front and back, and then just for insurance we put on the low melt solder and worked it in just to keep it liquid while we separated the silicone to make sure it didn't pull any pad from the bottom side of the board that we couldn't see. And after cleaning all that silicone up, we now have two boards that can go together back and forth easily. Now this top control board is going to be where our main problem is, and this is going to be our focus for sure. We have 4 failures that we know of. The bulge cap, which is pretty obvious. It looks like we go over to where this 0 ohm resistor goes across to what looks like a transistor, a SOT23 3-pin device, Q3. It looks like it goes on up and feeds this 8-pin device, U6, which is also a SOT23, and then this obvious 6-pin component here that blew out, U7. And this bottom board looks like it's going to be our 4 LED module controllers. So we got some filtering here, incoming fuse, and then our 4 individual LED controllers for each LED module. So I'm going to do the best I can to find some of these components and see if we can get this control board back going. So before we did too much work investigating those components, we did share that we took the LED modules, went across really quick here, just testing the LEDs themselves, and then we turned on our power supply and set it for 29 max volts, 200 milliamps max, to see if it will fire them off. And I documented that to be 27 volts. We're going to update this and have more information. Without much luck with components, decided to buy what Ego is calling the main electric assembly. The cheapest I found it shipping and all was from RCPW, so was glad to find that breakdown. And even though it's a lot of money for this part, it's $100 cheaper than a brand new light. So I thought for that price it would make a better video to see if we could find out the components or what they did on the board to maybe help somebody else in the future. So in that last video we did get our light back working. We just plugged that new module in, verified all the lights functionalities, and then cut into the new module, at least based off the old module. We don't have to go into it so blind about where the components are. Now you can tell I did dig a lot more silicone out than I had to, and that is just, in my opinion, better for heat. So I'm leaving it around the microcontroller, around some of the bigger caps and the inductors. I did pull a lot of that off. So here with the light on, we get to do some power on testing with this known good board. After studying the other board, I know that this side of the cap is also the negative rail. So as we go to this component that looks like a transistor, we get 12 volts coming from our main rail. We get right at 6 volts, so that's about half voltage of what looks like the gate pin, and then we're getting the 12 volts like we would expect. On the drain, if this is a MOSFET, if we cut the light off, we still have our 12 volts to what we think is the source pin, and then the more I think about it, 11.9 volts. This does make sense for a P-channel MOSFET, so it's being held low by a higher voltage, and if this drops, depending on the type of transistor it is, probably 4 to 5, in this case 6 volts under, we have a 6 volt delta, we do shut off, so that is making sense. Because if we check here, we'll just go to our back to our main rail here. I don't know if I even show this on video, but 12 volts on this main supply rail coming in, and we know that we go through our transistor and it goes up to this 8-pin chip. So we know which pin that is, and we know the output should go over to this inductor to the lower right. And we can see better here on this original board how this goes over, like so. So we have our power in and our ground, and then over here we have our feedback. It looks almost identical to the MP2315 step down converter chip. Our voltage in, our ground, our feedback, of course our switch output to our inductor, And of course that goes down to this 6-pin chip, which is absolutely a mystery. I don't know exactly what it's doing. If we go back to the working assembly, we definitely see our 5 volts at that inductor, so we know that rail is 5 volts, and it absolutely comes down to this 6-pin chip. So it comes through and we get our, what looks like will be our voltage in, 5 volts here, and it looks like we have an output of 0.8 volts, which is very odd. I had documented 1.2 volts earlier, so at first I wasn't sure this was anything to do with the USB, but now I'm thinking that maybe it is, and that something just isn't going right in this measurement, because if we look here on this board, it goes straight across, and oddly enough it's going to the black wire, even though this seems to absolutely be a positive terminal. So that does have me scratching my head, well, a lot. So the bad thing is I didn't test the USB output when I first got this module, and I have removed a lot of the potting, but I seem to have no issue, and I don't think I damaged anything. But still, anything is possible, and if I look at the manual, it definitely shows that the power button turns on the light, it will activate the USB, and then even with it off, it'll continue charging for about 2 hours. So the weird thing is this one is not even working now, but when I do plug in my USB monitor and I go across this resistor on the lower left part of the circuit, just with my meter in volts DC mode, I do get my 5 volts all the way out, and that is absolutely positive coming out of this chip to the black wire. It's like the polarity's backwards on the wire color, but you see now it's showing like 0.8 and dropping, so I'm not going to worry about it too much. But that is exactly why my USB was throwing me off. When I finally got to it to test it, I guess something wasn't working exactly right with it. I'm not saying all these lights are going to be problematic with that USB, but it is looking like it. So at this point I did post on our Facebook page on the bench, and I posted on there that I know it's a long shot, but it's a lot of smart people in this group, and I posted some information, as you'll see here, of what I found and what I was thinking, at least early on investigating. It did take me a little while to finally have time to write all this out and post it, but just trying to see if somebody out there had been through some similar things. And sometimes it's just having that knowledge of how they mark chips, and are the chips specialty chips, custom chips. It's hard to say for sure. Didn't have a lot of responses on it, which I really didn't expect a lot, and did have one set of comments here from Aaron. Aaron's a big contributor to the group, and his comments did help a lot because he was right there with me on the Q3. X11L really showed nothing to me. He did talk about it crossing to possibly a P-channel MOSFET, which was A+, exactly what I was thinking, so I do appreciate that confirmation. And for U7, well, we were thinking the same on that too. He said very long shot. Yeah, for me too, indeed. That's just a really weird marking, and I couldn't find anything on it. He talked about it possibly being a MOSFET. Just with the board layout, I don't believe the MOSFET's going to be what that is, and I definitely could be wrong. I'm almost 0% on anything at this point for that chip. And then he also gave confirmation on the MP2315 being the most likely chip for that U6, the 8-pin chip, and he even did mention that the MP2393 is a replacement, and it absolutely is. If you look up the 2315 datasheet, a lot of times it'll tell you that it's obsolete to not use that in a new design, to go with the 2393, but the 2393 is in a different package. That's why I know it's not that one. I think it's a SOT 583. But all very helpful, and I really appreciate his comments. So I placed my order with Digi-Key, and as parts are arriving, I go ahead and start removing the capacitor, because I do have a 47 microfarad 25 volt cap. This is a surface mount cap, but it does have the leads folded under. So I'm going to apply some heat here and then see if I can just gently lift this up. And if the leads don't break, I'm just going to snip them off. Just makes it easier to remove all this and makes those pads a little easier to clean up. We'll use some 99% alcohol and clean up, and we'll add some fresh solder to the pad, some flux, and we'll just set down this new capacitor really quick. It'd be nice to be able to use hot air, but hot air will make the capacitor pop, so I try not to use hot air around electrolytics. Let's go ahead and clean up these 3 pins for the transistor, because when it comes in, that's going to be the first thing I replace, and we'll go from there. Back now, Digi-Key came through, and this is what I chose to order. This Max 1920. At the point I hit checkout, I was thinking this might be the right chip, but now I'm pretty much 0%. The 400 milliamps is as high as I could find in this type of step down converter that fit this pinout. Very few had the in on pin 1 and then ground on 2, and the output being on 6. some feedback going in on 4. It all kind of lined up, and I don't even know if it's supposed to be a variable supply or not, but this chip would not come in anything 5 volts other than just variable. So I did give it my all on this chip and trying to cross it over with what information I had, but I'm already thinking this one right here is definitely going to come up short. Because one thing, even in the specs, it says plain as day this is a 1.5 amp for your USB device, and now I know that this is absolutely going over to the USB port, so nothing 400 milliamp even makes sense. So I don't think this chip's going to work at all. But on a brighter note here, we have the 8-pin 3 amp adjustable buck regulator. This is the 2315, and I do believe this is the correct IC. I'm probably 95% sure on this one. A lot of research, a lot of looking at the diagrams and typical applications, and it's just a great fit. If you take time to look at this, I have a picture up here oriented the right direction. The pinout is just absolutely spot on, and even their typical application here with the resistor network up in the upper right, everything but the inductor being about twice the value. I mean, everything is almost identical as their 5-volt output application. So kind of stoked about this. So at least we might get our 5-volt rail up. Well, I'm putting the cart before the horse. We got to get our 12-volt rail to it first, but so hopefully this is going to work and we'll get our 12-volt to it because of these. So I bought 2 different ones, one of each. This one's the 3 amp version, real similar to the one Aaron was talking about, the AO3420 series. And then I also picked a 6 amp Toshiba that's just kind of a little beast to be that small of a P channel. I'm only feeding a 3 amp buck regulator, but I don't know if this circuit isn't feeding some other things. So I just simply thought about, while I was paying the shipping, I might as well at least get one other type, and maybe throw that higher current one on there first, and then I'll have this other one that may be an exact replacement, but I'll have it as a backup plan. And I just believe these are correct because if we look here at our gate, source, and drain, it all matches up perfectly. And if we take a closer look here at our resistance on, drain to source resistance, with our voltage between gate and source being anything greater than minus 4.5 below the source, we're getting really close to max on. And we have about a 6-volt delta or differential between those pins, so I feel very comfortable that this P-channel MOSFET will turn on fully. So hopefully we'll have good luck with these. And just to brag about Digi-Key here a little bit, I mean, Digi-Key has to handle these things so small that if you drop them, you'll probably lose them. And they take time to put these in a bag. And, you know, sometimes I get frustrated about the $6.99 shipping. It costs more than my components. But at the same time, it's a lot of work to go through and cut a little individual component off to send it to us and bag it up. Static sensitive. I mean, so no affiliation with Digi-Key. I've just used them for years and years, and they just always have impressed me. They've always come through for me, and I appreciate them looking out for the little guy. I mean, I'm just a little YouTuber that works on stuff sometimes and buys a few components at a time, but just always glad to have them as a resource. So the first thing I done here was hit record on the wrong camera. So for a little bit here, you just see me looking right beside where I'm working with the microscope. And then I realized it, and I switched the microscope on, and there we go. That's a little better. So I heated this transistor back up here so you could just see what I was doing. I was just simply putting that transistor in place. And this is that 6 amp Toshiba P-channel MOSFET, 30 volt rated. The marking AJJ on this one. So that's what we look like, and that's how tiny this thing is. I'm going to go ahead and take time to put these boards back together so we can test. So I'm definitely going to fast forward through a lot of this, but you'll see that I'm just simply putting these boards back together so we can test and see if we're getting our voltage through that transistor. I don't plan on putting any other components on at this time, just one step at a time. Let's go ahead and get this side. Probably start in the middle. My smoke absorber is right above the camera, so you're getting to see a lot of it. Alright, let's clean up. We're just going to plug this board up so we can do some testing on the voltage rails. Get my meter up here so you can see it. So right now with the battery in, before we press any button, our 12 volt rail is good, so that's a plus. All we done on that one was replace the capacitor. And I really don't know if the 12 volt rail was down or not. Once I found the damage, I never did power this board back up. But we're getting our 12 volts all the way to our MOSFET source. And our gate has about 11.9 volts, so it is definitely turned off. And verified here at just 0.2 volts up here at the top. So I don't even know if this will work or not, since most likely the micro is not powered on. But I want to press the power button and just see if I get a voltage drop on pin 1 for the gate of the MOSFET. And as I press the button, I do get a drop at 6. Well, I got a voltage drop, but I was not expecting the light to come on. The light just came on. I was not expecting that. Sorry, don't pay any attention to the meter. I wasn't even paying attention to where the leads were. I was kind of in shock because the light came on. I have not even replaced the 5 volt rail chip. I was not expecting this repair for the light to be this easy, not by any means. So just a cap, the 12 volt rail, and then this MOSFET firing on the 12 volt rail. Everything's still working fine with this off. Yep, we got 11.9 volts holding off. Outputs 0.2 volts. Yep, that looks good. So somehow we're not even needing this 5 volts. I definitely thought the 5 volts then fed the micro, but evidently off the 12 volts we must be getting a 3.3 volt to the micro, because it's got to be powered on to keep the transistor on with the I/O panel, the push button panel. So it looks like all this from here, all this 5 volt, all this down through U7, yeah, it doesn't even go over to the micro at all. It's got to have its own supply, because this is feeding down just to the USB stuff. So this 12 volt rail must have been down. Replacing that cap got it up. I think all the USB power stuff took out the MOSFET, so I absolutely would never have dreamed just that one MOSFET would get the light back going. So that's good information. That's great knowledge to have right there. That, you know, people ask all the time, do we have a schematic? Companies don't give out schematics. You're on your own. So we try to learn what we can on something this complicated. To get lucky like this and get a little knowledge about it, you just tickle to death. So never would have thought that all that complication was for the USB, which I care really nothing about. I mean, it's good to know you can use it, but I probably have 4 or 5 things I can put batteries in and get USB power out. So even though it can be a plus, it's not a game changer. The light working is a game changer to me. So it's almost like having 2 different MOSFETs here, one for the light and then one for the USB controls separately. May have absolutely saved this light design from being, you know, problematic. So I don't know if I'm gonna fool with this USB at all, but I think I'm gonna go ahead and put the 8-pin chip on here and just make sure that I can get the 5 volt rail up. Before I do, let's make sure that even without the 5 volt rail, does the hall sensor still work to shut the light down? And it absolutely does. So the light itself is fully functional, which I figured it would be if the micro's up and the I/O panel's working here. The push button panel's working. So yep, absolutely. All that's working just fine. So I'm going to go ahead and put this 8-pin chip on here. Let's prep the pads. I've already got a little bit of flux on here. We'll just re-wet these pads a little bit. Oh, let's get that blob off of there. There we go. This is a tiny chip, and I do see now that I was calling that a IAGC, and I don't believe that is an I. I believe that is a line. So a little bit of knowledge really helps you with stuff like this. I really thought that was an I, but I don't know why they put a line there unless they were trying to show pin 1, but instead of a dot. You see the white dot on the lower right, that's our pin 1. Let's go ahead and clean up. 99% alcohol, and we'll use the brush as well. I'm going to go ahead and remove this 6-pin chip because it's faulted. I don't even want to power this on. It might mess up the 5 volt rail if I don't remove this chip. So for now, let's just remove it really quick and let's just clean the pads and everything's clear. So back now for our 5-volt rail check. The light did power on, so that's a plus. Everything's good with our 12-volt rail. Out of our MOSFETs, good. And we're getting to the chip. Let's see if I can get on there. Yep, on that side of the cap. That's good. And the output is going straight out to the inductor. And bam, there we go, 5.05 volts. Awesome. So that does have our 5-volt rail up. So that is 3 correct, or at least seemingly correct components in a row. This fourth one might be a failure, but we do see that we get our 5 volts to this. And then this will be where our output is going out and over to our black wire, which again is still positive. I don't know why Ego does what it does, but it looks like that is the positive rail going out and over. So if I wanted to bad enough, I could just simply bridge that 5 volts and I will probably get my USB power at least while the light's powered on. Not really important enough for me to do it, but I guess it's a possibility. I do want to take time to show here exactly where these chips are located. So physically, from the outer left side of this plastic housing, we're roughly 7.4, 7.5 millimeters over, which is roughly 1/4 of an inch. And from the top, we're down about 34 millimeters, which is about 1.32 inches. That will get you going straight in there to your problem if you had a transistor as well. I'll also take time to show up here these other components and where they're located by measurements as well. So that'll be Q3, U7, and U6 if you find that helpful. Another thing I want to do for reference here is show the voltage. I did this very briefly on the other video, but I definitely wanted to take more time in this repair video to share the individual module outputs. So I'm just choosing one at random. It doesn't really matter. This is the upper right module, so it's orange positive, gray is negative. We're in the lowest setting, 25.8 volts. We'll go ahead and step through here. 26.33, 27, 27.7, 28.27, and that is what I would call high. And then they have boost. So if you press and hold the plus button for 2 or 3 seconds, we enter boost mode, and wow, these things are really driving these LEDs hard. It tells you here in the manual how to get to boost mode, and it's pretty much telling you here that it does have a feature to stop it from overheating, so it may not stay in boost mode. It is telling you that anyway. But I personally wouldn't run this light in boost mode very much due to the heat, as well as the LED modules themselves being pushed really hard. So if you need it, it's there. If you don't need it, don't use it. I'm going to go ahead and remove one of the pins now. I'm just going to do the orange one. It doesn't really matter. I'm just going to go in line. I'm going to be able to show you the current readings. So take my meter and put it in amps, not milliamps, because we can probably go well above 400 milliamps here. Put it in amps DC. So now we just simply have our meter current shunt in series with this upper right module wiring. Lowest setting is only 45 milliamps. That would last a really long time on battery. The next step up is about 123 milliamps, and then we go to 243 milliamps, 363, 485, which is our high. So if we go to ludicrous or boost mode, we dang near double that. We 800 milliamps. That definitely would have blown our milliamp fuse for sure. We at 0.8 amps, and that was at almost 30 volts. So that is pushing these LEDs really hard. So, but I will definitely put that on a sheet for us to have a reference. We also have this spec sheet from Ego that tells us what the luminous flux is. That's what all 4 panels combine. Tells you what mode, what luminous flux, and then about how many hours of runtime. There is a little asterisk here beside 3 hours on boost, because it's telling you that most likely this light is not going to run for 3 hours in boost mode without shutting down to a lower setting due to temperature. So they are saying here that it's all dependent on your environment and temperature. So good to know. Let's go ahead and back this down. I don't like leaving it up that high for very long periods. And I want to share here all the information I've collected so far. So this is building on what we already shared in the last video. Now showing the individual module, testing and including that boost mode if you find that helpful. I'm going to go ahead and put my meter back to read voltage before I mess up and put it on voltage and blow something. This module does get pretty toasty. Even with a lot of that piping removed, it gets pretty darn warm. Just go ahead and connect our wire back up in our connector and plug it all back in. Just want to verify that everything does still work. do have to open that up, and there we go. So not a 100% fix, but I'm just stoked at how easy that was to fix, and really just happy that we did end up finding components to make it work. So that may not always be the case, so I did want to share in this video, if anybody wants to stick around, this is going to be like a plan C. So if things would not have went well, do we want to throw a nice light like that in the garbage? Absolutely not. So this is not the correct connector set, by the way. This is the 2.0, the 2mm pitch pH connector set, and this is just the one that I have, and I'll put some information up here in the top left on it so you can see the one that I have and what it's called. I like this kit because it does have all the different sizes, and I needed 3 different sizes, so I can make these work. But now the correct ones actually have the latch, and I'll share up here what they look like, and they are the PA. So JST, or Japanese solderless terminal type PA. They seem to be the one that has the locking tab. I've never actually bought those because I don't see them as much, but that is the ones. If you're interested, I have taken the time to make up part of the set that I need to run this light. So I put together the colors from the wire that actually comes with it. That's the right size for the pins. So this is the one I made up for the power. I'm only going to use the positive and negative terminals. I'm going to use both wires. And then I made up the other one with the correct color code as well that matches up. I also need to make up a yellow and white one for the main module. I did have to cut the spot where the locking tab goes on this one. So as you can see here, it was like this one on the right, but I have cut it out. Just took my razor knife and sliced it out, and that way my locking tab can slide down in there. Let's go ahead and strip these wires back, and let's make this cable up really quick. We're going to get our wire lined up with our pin. I'm going to bring over these iWice crimping pliers. These are some of my favorite crimping pliers for these small pins because they are some of the thinnest that crimp like this that I have found. I have bought many others, and they're so wide that they affect your very top of these pins, and these just seem to work really well. So I'll make sure my insulation is on that bottom crimp. Sometimes you kind of got to close them up a little bit so they'll fit in the U shape of the crimping pliers correctly. I'll try to ease this down so maybe on video you can see the detail of those wings folding in. And I'm going to leave this a little bit loose like so and slide it all the way down to make sure the insulation is captured by the lower wings. I'm going to turn it and just get it just a little bit captured better, and then I can put it in the smallest one. And this size wire seems to be better with the smallest size crimp. And we'll just make sure that that rolls over and does crimp well. You want them to come over and just kind of roll into the wire, and that the wire is in that little middle wing. I think some people confuse those top wings to be crimpable, but they are not. That is your alignment and your latch. And then just close the wings in on the insulation, and yeah, close them up a little bit more, and then we'll go to that second size, get it lined up. There we go. That crimped pretty well. Might want to push that down, maybe go up a size and just round that off a little bit. Yep, that actually helped it bite in pretty good. So now that rolled around into the insulation. That helps so much with these small wires from breaking off at the connector. Just captures and gives it a good strain relief. Let's go ahead with the white wire and let's crimp it. Just going to close those wings up around the strands of the wire a little bit to capture them, and then line it up and just gently press. I'm going to go back and forth here pressing, so hopefully on video you can see how that rolled and crimped in. And then on the insulation, going to fold those wings in a little bit, and I may even go up one size to get it started. That actually crimped okay in that size. So since that insulation is thicker with these real fine wires, sometimes I will do that. If you can see that catch on these, on the opposite side of those little upper guides or wings, that's why you don't use those to crimp with. They're like guides, and there's your catch on the very back. So it goes up and just snaps in like so. Same with the white wire. We crimp below where that tab is, that little locking tab. So this is the polarity we need here. just like so. So now I have all three of those made up if I need them, and I will have links in the description for similar tools like these strippers and crimpers, as well as the connectors if you're interested in some of the information on those. So for example, if we take our yellow and white newly made connector and we connect this up, now we can power up that main module, and we can also do the same thing with this other connector I've made up. It looks like it goes this way, but actually because the latch is not on this one, it turns and goes this way. So that's not intuitive. The latch just slides on there and it doesn't latch, but it does fit snug. And you can see here my color code does line up. If I wanted to power these other modules with the reference sheet that we have with the information on it, we can do so. I also have the power. By the way, the battery's not in it, so if I do plug this up, I don't have 56 volts just dangling around here. But that's obviously something to be aware of. That's how that works, and it does hold in there pretty well even without the locking tab. It is still the 2.0 JST terminal. They just don't lock. Best to get the right ones. But I use red and black here. Obviously, for whatever reason, Ego used blue on the negative as I showed on the reference sheet. We don't actually need the D or the T terminal. We're just going to take the power into a DC to DC converter or some other type of LED controller module. This is just an example one that I have that I really don't recommend it because it don't have a good heat sink or a good way to dissipate, and it's going to get really hot. So the good thing about this one is it is rated to over 60 volts, and I believe it's 3 amps, and of course it is current controlled and voltage controlled. So that is a plus, but it don't have good heat dissipation. And we just got to think, we're going to dissipate half of this as heat. So we're taking 56 volts to around 28 volts. So we're pretty much dead center. But we could definitely use this. You would want to use one buck converter module for each LED panel really. And that would just take up extra space as well as more heat dissipation. But it could be done. It's got enough current that you could drive 2 with it. You would have to be all on voltage control at that point, because current control, if you lost one module, you could damage the module if your current went too high. So you would have to limit your voltage to, like, say, no more than like 27.5 volts and just go with it. If you lost a module, the other one still be 27.5 volts and wouldn't hurt it. But we would just put them on here like so. Yellow to plus, white to minus. And I might show that before the video's over, just briefly how that would go. But for now I'm just going to bring up on my power supply, because really, so as long as you put the positive to yellow and the negative to white, and you keep this no more than 28 volts, will be okay. Remember, it takes over 24, 25 volts to even fire them at all. So it is important to keep the voltage at a steady rate so they'll be bright enough, but you just don't want to go too high. So these right here work okay, but you will need more of them. They do make modules like this. This does have a nice heat sink, and it is large enough to actually run all the modules, but they would all be in parallel, and that's just not the best way to do it, but it would do it. I don't know if it will need a fan or not, because it will be dissipating half of that wattage. So is this only driving 28 volts or so? But it's at least an option. It don't fit in that spot exactly, but it would have to be like mounted outside of the light, just as a makeshift get the light back going type ordeal, Just an example or a thought of something that will be a plan C and easily done with the connectors. But instead of having 4 of the modules, you would have all 4 on that one module and totally be on voltage control, which isn't the best for the LEDs. But if we drop it down a little bit, they would last a long time. So I do have this main module hooked up to my power supply over here, and I will put the video of the front of my power supply up here on the top left. Set at 28 volts and 200 milliamps. We cut this on, and as we documented earlier, at 200 milliamps we run right at 27 volts. That's how that regulates, and we're talking 5.5 watts. So you're going to be dissipating about 5 to 5.5 watts on whatever device that's limiting that, if we're putting in 56, 58 volts. If I bump my current up to say 0.4, we're going to limit at 28 volts. That's our upper voltage limit. We're not going above 350 milliamps at this point, almost 10 watts. We would have to jump up our voltage a little bit to give us room to get above that 400 milliamps. Just going to open this up. I don't want to wash out the video, but I want you to be able to see the intensity change, if that makes sense. We can go up to 500 milliamps max. We're going to have to bring up this voltage. Yeah, roughly 29 volts, and 500 milliamps is where we stopped at. at roughly 28.5 volts, and that's still driving these pretty hard. I really wouldn't want to drive them quite that hard constantly, but that is a good bright light. But as Ego has showed us, in boost mode you can even go up higher to 800 milliamps roughly. We'd have to take our voltage on up. We're not there yet. 29. I'm not going to quite go to 30 volts because they limited right there at maybe 29.8, 29.9. So that's what this module is showing, right at 23 watts. So that's what you'll be dissipating on a controller that's putting out 27, 28 volts with 58 volts input. Probably going to have a fan on it, or at least it'd be best to have a fan on it. So really quick here, we do hook this module up. I got 55.8 volts going in. I soldered on the yellow and the white, the right polarity here, and I have my potentiometer set for output voltage to be 28.5 and roughly 300 milliamps max, so just a little above middle of the road on output. I plug this in. We see our light went from green to red. We're in current control. That means our voltage has dropped down slightly, but that's good. We're controlling at 27.4. So even in variances in heat, things of that nature, we still should limit voltage and current to be in a safe level. But just running here for just a short period of time, if we take the FLIR camera and we look, we're already running at nearly 70 C. So we're close to 160 degrees Fahrenheit. So that's what I was talking about that module. Might need a heat sink, but it is a possibility and a possible plan C to use something of that nature. So that's one thing that I really, really love about working on something that I know nothing about. So I started with this thing with zero knowledge, and everything we've learned through these 2 videos has been 100% gain. So 100% gain in knowledge. Not 100% of what it should be or ought to be, and not 100% of where we will be, but it's 100% more for sure than I started with. Definitely wanted to take you on this journey and share it with you today. So hope you found the video helpful. Thanks again to Steven for sending this light in to us. It's just been a fun project to learn more about. So I hope you found this video helpful today. If you did, please like, share, and subscribe. I'm going to have some links down in the video description for a lot of the items that we used here today. If you find it helpful, a lot of those links will be affiliate links, and they help support the channel, and I greatly appreciate it. Thanks so much for watching, and God bless.